Hey everyone, so I was thinking, what can we talk about? Okay, then I realized that I think it's a good idea to talk about imaginations and talk about what I'm thinking, how it goes to a computer screen, and all these things, right? So now think about it. We already had a discussion, right? So this is a linked list, okay? This is a linked list, right? This is a linked list. And imagine there is a data in here, okay? This is a linked list, this is null value, and this is the head. So head is, basically the first node and the head is basically the same thing. So H is pointing to this. So this is the head basically tells us this is the start of the list, okay? We shouldn't even call it head. I think I'll prefer to call it a start. So if I say start of the linked list is, let's suppose, A. If I say let's start from start, that actually means I'm starting from here, so you can iterate. Okay, iteration matters a lot. Okay, now, so this is a linked list object, and how did a linked list object look like? It looked like this. So this is the box that the constructor gives us, right? And then inside there we have one pointer that points to a data location, right? We have another pointer that will point to a node of a linked list, right? It can be any node that you want, okay? And you already wrote functions and all these things about this. You can look online, have a look at the code. But the most important thing is what can we do uh, to understand this? You see, these are just two pointers. We can literally start writing that data is equal to this and next is equal to this, but that's not going to work. That is the concept of an object or object-oriented programming. The class constructor gives you that box. Put both of them in the same in a location, let's suppose is memory locations, and put a box around it, and then this itself has a memory location, right? Now let's see, another data structure we have is a stack. Stack is first in, last out. Just like you stack plates, right? We have a stack. This is how we show the stack. So you have here a node. Let's suppose you enter A, then you enter B, okay? You enter B, then you enter C, right? And stack has operations. One is pop, one is push. So if you want to pop something, if you want to pop A, you must pop B, C, B, and then you will reach A. Okay? And there's a lot of uses of stack that we do in a binary tree and others in other places. So what can we do? What is a stack? How can you have a constructor, an object of a stack? Nothing. This is our stack. This is what we need, like this, right? But how can we tell the computer this imagination we have? So let's suppose you have plates, right? You put, this is one, another plate over, another plate, another plate, another plate, right? And all of them have names, right? You can put anything, or you can put boxes. So you have box 1 here, and you put box 2 over the box 1, box 3 over box 2. So logically, in a real life, if you see, if you want to reach, if these are boxes, like, right, if these are boxes, imagine now this is some kind of a surface. These boxes are there. If you want to reach box 1, you cannot get just box 1. You cannot get it directly. You have to remove box 3, then box 2, and then you have to reach box 1, right? So that is the thing. And if this is the situation, you have these boxes, and if you want to put another box in the same location, yeah, This is basically a stack. I put box 4 here, right? But what if I put a box here, right? In a real life situation, this is location 1, this is location 2. So you just created another stack. Then you put box 2 over it, box 3 over it, like the same way, right? So this is the imagination. Now, what do you think? How does the constructor look like? What is the constructor here? What is the object? So this is where come the one thing more. This linked list, the Python list is almost the same thing. In Python, we use list as a as a and we can use list as a stack also. Okay. Now, see, imagination. You have a surface. The moment you start placing boxes, just imagine that you made an invisible two lines around it and you are placing boxes here. You're placing boxes like this, right? So this is basically a list. You created a list, right? So the constructor will have nothing. Computer, the constructor inside the class of stack. This is the constructor gives you the box and it will have just one pointer to what? This will have a pointer to a list. That's it. This is the object of a stack. This is a stack. This is a stack object. This is a stack object, right? Now, so this is a stack object, okay? And we can now go to the stack has push and pop, and you can know the size of the stack. So what is the size of the stack? The size of the stack is basically the size of this list, right? The length of this list, right? Now what we do, we're gonna go to another data structure, uh, which is basically a queue, right? So what do? Queue. You stand in a bank line and we made a queue. Whoever stands first in a bank, he gets the first position. Then the second person stands, then the third person stands, right? Sorry, I wrote it there. And so on, and the nth person will stand here. So we are basically moving like this, right? So when you are standing in a bank line, what did you do? Basically, an imaginary kind of a list is created. This list, and this list. Okay. Now, this is an horizontal list, right? This is vertical. Stack, we create a vertical list, right? In here, we create a horizontal list. That's it. Starts like this. Starts from the front. As we move on, we have the lines ready, right? So in here, you see, if I put a box here, then I can 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 put a box here. So these boxes I can put as much as I want. But the rule is, this has a use case, okay? You can, excuse me. The thing is, the rule is that I can only remove from this end. Whoever is first, that's gonna be accessed first. Removal is basically the access, right? So you can remove it from the stack, you will have access to it, right? And then what happens is, if you um, and this way there is a double-ended queue also. We're going to talk about that later on. So this is a queue data structure, okay, that we can use in a lot of places and a lot of problems and all these kind of thing. And I know you have a very major question. So why do we need data structures? What is going on in here? Okay, and we're going to talk about that in a bit. Let me remove that. And now, why I'm trying to show you different kinds of object, because my idea is that um, to have our imagination connected to the idea of an object. Okay, now another thing is, we have a tree data structure. Okay, so what is a tree data structure? So we have a, right, and then a, connected to B, connected to C. This is binary tree, right? This is the parent and these are the child. This concept is applicable in anywhere. Even in a for loop, you see the top for loop that you write is a parent, and then there is a child for loop, and then there is a child for loop, right? Now see, so A, B, C. B and C are the children of A, right? So now it comes the idea. So what happens is this is required for, so imagine this is a computer memory, right? Binary tree is a very good data structure. Data retrieval is fast. I'm not going to go into complexity um, to confuse you, but what I want to say is the the thing about data structure is that it's just faster retrieval of data. Today everything is about data, right? We have gigabyte terabytes of data produced every second, and businesses are working on data, right? And we do tons of analysis and all these kind of things, tons of machine learning models and stuff. And what happens is we need to model them in a right possible way. So basically, if I redraw this in a different way, this might be, this may be address 3, this may be address 3000, right? And this may be at address 1. But it's pointing to this and it's point, there is no left and right. We just call it like this to make it sense to ourselves, right? So how does an object, how does a node of a binary tree looks like, right? This is an important question that we have in here. So a node of a binary tree, always we got a box, constructor gave it to us, right? You can, this is my own metaphor, okay? What do we have? Nothing. We have one variable pointing to a node. So I have a variable called right. I have a variable called right. Sorry, that was bad. And then I have a variable called left. They can point to another object. You see, this is an object, this is an object. And then, because this is an object, it has the same structure. You see, so this is basically a binary tree node, right? And it will have a left pointer and a right pointer, and it will have what, this is one thing else which, see, imagine I missed it. One thing else is the data. It will itself also save a data, right? Like this node is saving this data A, basically that is this. So I can have a node like this. Let's imagine it has left. At this moment when I make it, it's null. So I'm gonna show null by this. But this one has data because I give it A. So this is a binary tree node. We have one node which is called A, and the left and the right pointers right now are null. And then we can set these pointers to point to another node. Okay? So this is the idea. And then I think we also forgot to um, the queue. The queue is basically the same thing. You have a list. You have a list, and then you can have the front of one variable for front, one variable for back. You can have a variable for counting the each data in there, right? Um, so this is the fundamental idea of an object. Okay, now we can go to other objects also, right? And just you have to think about it, you have to look around you. So one of the important thing in here to remember is um, the design aspect. Okay, we have to imagine something and say, oh, I have this object and it has this and this and this characteristics, and how can I design this object? Okay, and this is a very good idea about understanding about, and then like this object belongs, this is a node object, right? This itself is a node object, and then it's going to be part of a binary search tree or a binary tree. And then you will have a class of a node, and then you will have a class of a tree, right? And it's gonna you will, by the end of the day, you will build a tree, right? But the thing is that what we need to understand is, why do we use data structures? Faster data retrieval. Think about it. Yeah, I'm sure you know about databases and all these things. Hey, we are saving data in a database. Why do we need data structures? Yes, because to perform operations on something, right? When you are running a function, or when you are running lines of code, for example, if I access the database times and again, what happens? It's very expensive for the memory and for the speed, and we wouldn't have this much speed if we would do that, right? And then the cache and other topics, very advanced topics, are a different thing. But in now, if I have a function and it's doing a certain calculation, let's suppose I have an array, right? Let's suppose I have an array, and I go through an array, do certain operations, and if some condition is met, I need that value. So where should I place that value? For example, I may not need that value to insert those into my columns in a database. So what I do, I put that value in a data structure depending on your own design. So for example, I go through this array, I find something, I put in a tree, right? And then the left, right. Or for example, I say this first is the root of the tree, right? The root of the tree. And then I have a condition, I have my own calculation or business logic, and then I move on and put that value here and put that value here, and so on. And finally, I will have a tree. Then after this first step, whatever processes you have done, you can access your function return, whatever it has given to you here, and then you can perform certain more operations in that, and by the end of the day you have a return value, and you did your work, the function did its work, and you didn't save data to the database because it was not required. Why would I save something if it's not required, right? So guys, we had looked at object. Try to understand it, try to think about object, try to imagine it, try to for example, I may explain to somebody an object like this. I say, hey, let's suppose a binary tree object. This is a memory, right? This is a memory, and I have one node of binary tree here, right? I have another node. Imagine this is, I have C here and I have B here, right? Now see what happens. Uh, Now I want A, this is address 1, address 2, address 3, right? Okay. Now what I do, I take this, right? I don't know why I get this. Anyway, so A's left is the B or C, it doesn't matter. I can say A's left is pointing to C, this is left, and I can say A's right is pointing to B. But in a binary search tree, there is a condition there that the left tree, because that's how it's faster. We made a smart decision, and we said, well, I don't want to go through all the tree, and a certain way was made that, okay, the left tree, the value of the left tree will be greater than the value of the root, and the value of the right will be greater than the value of the root. What does it mean? In this way we have string, that's fine, this can be happen in any binary tree, but imagine these are integer values, right? So for example, if I have 13 here, now I have two values, 10 and 20, right? Now where can 10 go? 10 will come to the root, root will see it's less than me, it's gonna put it here like this, and then 20 will come. 20 is greater than this, root will put it here, right? Now if I put 30, what will happen? It will come to the root. You have already written a function adding to a binary tree. It says it goes to the right, but then we have another node. It's going to ask, hey, this node also. This will say it's greater than me. So this will be here, 30, right? Now if we got 1, 1 is less than this, will come here. Then 1 is less than 10 also, so it's going to come here. If we get 12, it's going to come here, and then 12 is greater than 10, it's going to come here. You see, we have a binary tree. Okay, so think about these ideas and try to give it sense. Try to get objects around you. Let's suppose the deck of cards. Let's suppose these are very famous examples. Let's suppose about a Sudoku game. Let's suppose any other games that you have played, and see if you can create objects of those 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 things that you are thinking, right? Um, then now for example, I just give a quick last example, which is the object of a card. If we are playing cards, what object do I have, right? I have, so this, right? I will have something called the suits, right? Which suit I have, this will point to it, and then I will have another thing. Let's suppose the rank, right? This is my card object, right? You have 4 suits A, B, C, and then you have rank, so it goes in that way. But I'm gonna make more videos, and we're gonna talk about this, and we will try to also code it. But I'm gonna now more talk about um, working on our imagination and trying to simulate the real life scenarios, how we can think in terms of computer science or in terms of a computer itself. Okay, so guys, that's it for this video. I will see you in the next video. Okay, bye bye.